Welcome to this video on nuclear fusion. In this video we're going to be taking a look at the process that is almost the opposite of nuclear fission, which we looked at in the previous video. Again, I'm going to be using images and example problems from the openstacks.org University Physics Volume 3 text, and there's a link in the description below so you can access the awesome resources that they have available. Thanks as always to them for these awesome resources. So we're starting with the graph here that we looked at when we first started looking at nuclear physics. And the graph again is the binding energy per nucleon in mega electron volts versus the mass number. And basically what it's showing here is the relationship between the amount of energy needed to break apart a certain nucleus based on the mass number of that particular isotope. Now, what we see in this, as we looked at very briefly before, is that iron 56, this isotope of iron, is considered to be the most stable nucleus. And although we have a small region of plus or minus 60 for our mass number, that is considered to be the Goldilocks point, or the just right size for a nucleus. Now in the fission videos, what we looked at was that bigger, more massive elements would break down, and they would fall apart either naturally through radioactive decay or through the force process of a nuclear reaction where we bombard these larger nuclei with neutrons. And what we see happen here is that energy is released in this process. And the energy that is released can be used to do different things like we talked about before. And we refer to these as exothermic reactions because they release energy. Energy is exiting the reaction. On this side, what we're going to be looking at in this video is fusion. And actually, a very similar thing happens here, is that again, we're going to have an exothermic process by which the nuclei of smaller atoms actually combine together towards the iron 56 isotope. Now, this will occur naturally or spontaneously in nature, and in fact, it's one of the main hypotheses to how all of the energy that is generated by stars occurs, and also how most planetary systems actually form. But it can also be forced through hydrogen fusion. And in fact, the main mechanism that we're going to look at today is referred to as proton-proton chain fusion, which is basically one of the hypotheses for how our sun produces energy by fusing hydrogen nuclei into a more stable helium nucleus. So basically what we can say is that as we approach iron 56 from either side of this graph, the nucleus becomes more and more stable. So in other words, it's essentially more stable to be oxygen than it is to be helium or hydrogen. And it's more stable to be krypton than it is to be uranium-238. But why is that? And how is it possible that combining nuclei produces exothermic reactions as does breaking them apart? So that's what we're going to be taking a look at here. Well, one of the main things is actually in a theory that we haven't talked about in great detail, and that has to do with some of the four fundamental forces of physics, or four fundamental forces of the universe. And those forces are the gravitational force, which we know is pretty weak compared to the others. We've looked at extensively the electromagnetic force, which is pretty strong compared to the gravitational force. And now we're going to look at one of these other two, which is actually the strong nuclear force and the weak nuclear force. And what we are looking at today is really the give and take between the electromagnetic force and the strong nuclear force. Now, this scenario that we're going to be discussing here is sometimes known as the semi-empirical mass formula, which basically tries to show how an atom or a nucleus specifically will form and the energy of that nucleus based on the mass number and the atomic number. And what it basically says, without getting into too many details, is that there's several sources of the energy that form the nucleus. We, of course, are going to have the electromagnetic repulsion, and this, again, the repulsion is because we have protons that are next to each other, kind of crammed right up next to each other, and we know that opposite charges will naturally repel one another. But then we also have the strong nuclear force, which is the force that's going to be responsible for holding together things in the nucleus. Now, we have to rank these again according to strength. We know that the gravitational force is fairly weak, so even though we have mass right next to each other, it's not going to contribute very much here. Now, the electromagnetic force is very strong and is stronger over greater distances. So when we look at things that are far, far away from one another, the electromagnetic force still has an impact, whereas the strong nuclear force is really only good over tiny distances. So in other words, it's much stronger than the electromagnetic force, so we could say 3 is much greater than 2, but it only acts over small distances. So let's take a look at that according to the structure of the atom. So let's start with a large nuclei. The size of the nucleus means particles on one side of the atom versus on the other side of the atom don't have as much pull from the strong nuclear force on one another because they're at a greater than the tiny distance, which is the optimal distance for the strong nuclear force to act. So here's a little example. Let's say that I have a chain of molecules, and this again is just an analogy. And I have molecule A over here and molecule Q over here. Molecule A is interacting with molecule B through the strong nuclear force, a little less with C, D, E, and so on. And as this gets to be longer and longer chain of molecules, the strong nuclear force has less and less an impact on this side of the nucleus to this side of the nucleus. And so what ends up happening is that you might get to a point where you've hit this critical length, it just cuts off in the middle and kind of falls apart. Now, the strong nuclear force is much stronger than the electromagnetic force, so even when you have molecules that are really close to one another, even though they're trying to repel one another, the strong nuclear force is overriding that and keeping them together until they get to the point where it's too big and they'll naturally fall apart, and we'll see them move towards this state. Now, the side for fusion kind of is the flip of that. For small nuclei like hydrogen, maybe helium, if you're able to add more nucleons, they're likely to stick due to that strong nuclear force. And this is why smaller nuclei tend to fuse together. So sticking the particles together results in a lower energy configuration, so it's more stable. But as you add more and more protons or nucleons into this, they're going to repel each other more and more and more until they hit a point where they're not at their best in terms of balancing out the strong nuclear and the electrostatic force, and they will separate one another. So iron 56 is the gold standard in the sense of it's the point at which you have just the right amount of repulsion and attraction to where it stays the most stable. So remember, even though binding energy refers to the term binding, which is putting things together, binding energy can also be seen as ripping things apart. It's the energy needed to break the nucleus. And we can see here that iron 56 requires the most energy to break it apart, and therefore it can be said to be the most stable. I sometimes think of this in terms of a bundt cake pan, and bear with me here on this analogy. So if you think of a bundt cake pan, you have this opening in the middle that gives it its characteristic shape. And the idea is if you pour cake batter into this, it will keep filling up until it hits its maximum amount, after which it will start to pour over the edges. And so you can think of it almost as though there's two sides that will return the batter back to its original spot. If we fill it up over on either side here, it's going to either pour over or through and not be part of the bundt cake pan anymore. The batter will have spilled over the edges. But up to a certain level, we've hit the perfect amount, and that tends to be what iron 56 is. Now again, this is just an analogy to think about the fact that there is the perfect configuration. If you're too big or too small, you will move towards that point because of the natural attraction and repulsion of the nucleons. You can look at this in a lot more mathematical form through the semi-empirical mass formula, which we're not going to focus on in this video. So the very last thing I want to do here is just take a look at how stars, will form a chain reaction here to fuse nuclei together. So this is referred to as the proton-proton chain reaction. And what we're basically going to do here is find some hydrogen that is available to fuse together into a slightly heavier hydrogen. And in the process of doing that, what's going to form is a positron, like we did in beta decay, a neutrino, and a lot of energy. Now, some of these free hydrogens that are floating about are going to will form a compound with this heavier hydrogen as well. And what starts to form now is an isotope of helium. So this is a chain reaction of events. We get this first reaction, then the second reaction, which actually produces gamma radiation and again energy. Next, after that, this helium isotope here, helium-3, will then bond with other helium-3 atoms and will end up forming the more stable configuration of helium-4, which is our valence form, and the two extra protons will form two extra hydrogen atoms, and then of course more energy. So if we wanted to combine this chain reaction into one statement, what we could show is that 4 hydrogens will form into a helium nucleus, and as byproducts to that, we'll have positrons form. We'll also have gamma rays released. We'll form neutrinos, and of course heat. So basically what you can do is, by conserving the nucleons and the energy, the mass energy, you can again find the mass defect between the mass of the reactants and the mass of the product, so the difference in that, and this of course will give you the amount of energy that is going to be released through the reaction. So every time energy is released in the reaction, it's going to be able to be compounded together, and this is what produces enough energy to help support a star. So to end this video, I'm going to show you an image here. Let me scroll down to it. We have this image over here, which is actually a representation of a star, where the gravity is trying to, or is naturally coming together, which is would collapse the star, but this force that's created by the fusion process, this external that's pushing outwards, will create this balance. Eventually, as stars go through their life cycle, they'll fuse larger and larger elements, getting towards iron, and eventually, when they burned out of all the possibilities, the gravity will become greater than the fusion, and they will collapse. And when they collapse, if they're large enough, they'll create a supernova, and that can create many other cool things like planetary systems. I recommend highly watching and reading some documentaries on that process to apply some of this basic knowledge.